So, hello everybody. My name is Walter Kovacevic, and shortly we will begin with a presentation of the gear analyzer and gear software. We have some seconds left, so I think we should start at the scheduled time, which is 3:45. And I hope you'll enjoy it, as I do. And yeah, okay. So I guess we should start again. Welcome, ladies and gentlemen. My name is Walter Kovacevic, and I want to show you the gear and WM gear analyzer software. So some words to Wensel. Wensel was founded in 1968. There's a turnover of more than 87 million euros, and employees more than 650 are on 17 locations all over the world. And we have more than 50 sales and service partners, 5 product lines, and we have more than 10,000 machines sold. And our impressive research and development intensity is more than 11%. And our goal is the 100% reliability. So what will we talk about today? We are talking about the WM gear and gear analyzer, which is a solution for involute gear measurement and evaluation. We'll talk about the supported Wensel hardware. I'll show you a live data entry example on WM gear. And we have some pre-recorded measurements, some videos pre-recorded on a LH87 with and without rotary table I will show you. And after the measurement finished, the gear analyzer comes into play. And the gear analyzer analyzes and produces diagrams. And I'll also show you the gear analyzer live with a diagram example and things we can do with it. And the short summary will finish my presentation. So the gear, WM gear, and the gear analyzer is Wensel's solution for involute gear measurement and evaluation. It covers internal, external involute gears with profile and flank modifications. And it evaluates, presents, measures characteristics for profile, helix, pitch, run-out dimensions over ball, pins, tooth thickness, root, tip diameter, all the characteristics which can be determined on an involute gear. And the program is very, very easy to use. So for example, there's only one input page necessary as a minimum data input. All the other characters, all the other parameters are suggested by us, or at least we hope so, meaningfully, so that a complete measurement and evaluation can be done. And this ease of use simplifies the entry for a newcomer for that software extremely. So we use, therefore, pretty simple dialogues, and we try to hide complexity if not needed. So the power is there, but it's not in the foreground if you do not need it. And we are extremely flexible in definition of measurement jobs and tooth modifications. I'll show you later. And of course, we do not want to invent the wheel a second time, so we try to reuse existing solutions. For example, the CMM kernel for machine access, or Quartis for probe management, determination of coordinate systems, and so on. So let's continue with the supported hardware. Software runs on Wensel LH machines with and without rotary table. So there's no absolutely need for a rotary table to run the software. We can check nearly every gear on machines also without rotary table. And the program is tested with a Renishaw PH10 SP25 combo. And especially when we use the PH10's rotation axis and with a L-shaped probe, we can easily check the gear on machines without rotary table. It's also tested with the SP80 probe head and up to 8-fold star probes. Okay, I'll show you an example of a gear data entered with the gear software, and you might have seen this small panel here. We call it program switchable panel. You can position it everywhere you want, and this simplifies the switching between Quartis, gear, and the gear analyzer. The programs are all running, so you can switch Quartis, gear, gear analyzer, force and back like you need it. There's no need to restart software and stop software. Just switch to the proper software you're trying to working at. So we're in the gear software, and that's the main screen. I talked about this screen. The data with the data from that screen, from that window, we can check, evaluate, and present a gear. So what we need is the information if it's external or internal gear. Easy to define. So we need the number of T's, the normal module, or respectively the NDP for our American friends. So you can just switch forth and back which value you have, and the other is automatically derived from the other one. If there's a tandem modification, you can put in the modification itself or the modification factor, just what's on your data sheet. So we need the pressure angle and the helix angle. If it's a straight gear, helix angle is 0. But also you can have 15 degree or whatever it is as a helix angle, right, left-handed. From this information here, we compute the base circle diameter and the reference diameter and the V-circle diameter. Typically, these diameters are on a diagram on a data sheet too, so you can double check if the data you've put in here is correct, and when the same basic circle diameter and reference diameter appears as on your data sheet, it should be okay. What else do we need? We need the tip diameter, which is here. You see it's clearly marked. A is tip diameter. In that case, it's 45 millimeter. We need the root diameter. That's a root diameter here. And we need the face width. That's all we need as a minimum. If your gear has some stop shafts on reference or non-reference side, put it in here. If not, that's not needed. There's another mark you can do here. Left flank equals right flank. If I unmark that, we may have different informations for left and right flank of the gear, but the majority of gear is equal left and right flank. And to simplify data entry, just click here, and you only have to input the data on one flank, and it's automatically copied to the other. And the last thing, which is pretty important, I think, on that page is if the tooth count is clockwise or counterclockwise, because this is sometimes pretty important if you want to compare diagrams from previous measurement, from a competitor, or from where else you will have a diagram. And if you can decide if the tooth count direction is clockwise or counterclockwise, you are able to find the same T's you want to check as on the other diagram you want to compare. Okay, let's assume this is not just a simple gear, it's more complex gear. It might be a segmented gear. Segmented gear means that our T's are missing, for example, tooth number 3 and tooth number 8. So just click on the T's you want to make disappear. Click again to make it reappear. Or there are gears with missing gaps. So let's say the gap between tooth number 4 and 5 is missing, just click here. And also the gap between number 8 and 9 is missing, just click here. Click again, back to the normal gear. And if I would have a gear, let's say with 100 T's, the gear would look like that. It makes no sense, and it's pretty inconvenient if you would click on every tooth you want to make disappear with a gear with 100 of T's. So therefore we have some pattern. Let's say we have plus plus, minus minus, which means there are 2 T's available. The next 2 are missing. The next 2's are available. and voila, we are here. 2 T's available, the next 2's are missing, 2 are available, the next are missing. So it's pretty easy to define segmented gears. We have a lot of more other tools I could show you here, but I think that's enough for the segmented gear. You see, I go back to the, let's say, original 10 T's gear. You see the counting here is 1, 2, 3. It's counterclockwise here. We go in the basic geometry and say, okay, this is a gear with clockwise 2's counting. You see it here, 1, 2, 3. Now it's clockwise. So let's continue to the profile. You have the typical data from start measurement, start active profile, end active profile, and measurement. So that's the basic information for the diameters on the profile. Now we need some information where and what to check. So typically a profile is checked in the middle of the tooth, in the middle of the flank. You see this line here. This means Z equals 0, and at the middle of the gear, left and right flank. And the profile might have some modifications. For example, profile crowning. And the profile crowning here, which is on your data sheet. Or you might have reliefs. This is a little bit more complicated data. And you see there are different values you can put in to define, let's say, a tip relief. And also when you look here at this part of the diagram here, you see in that case, the tip relief is from the nominal value. And if we select variant 2, this is the extended regression line extended to the tip diameter. And in that case, this is the tip relief. So because there are on different companies, specs and requirements, the reliefs are not clearly defined. So we found different definitions of reliefs, and we try to realize that. Switching back here, you see the graphics here is changing. So you're always clear when you have a diagram, when you have a data sheet where the reliefs are marked, perhaps like here, then you know which variant you have to choose and to enter the appropriate values here. So every time when it's necessary or helpful to have some diagrams, we try to provide diagrams. Okay, these are modifications, but then sometimes you do not only want to have one profile checked at a tooth. Let's say you have 2, 3, 4 profiles checked. Typically, of course, at different positions. Let's say one at 5 millimeters, one at -7 on the right flank. It's -2. So you can do as many profiles as you want, and I'll just make it back. So it's just up to you. If you have some special requirements in number of profiles and positions and where to check it, you can define it here. So these are the positions on the tooth. And on that part of the screen here, you see which T's you want to check. This is the T selection. Typically, you have 3 or 4 T's you want to check. Just select it here, and the 3 T's are marked, which should be checked. But also you can, let's say you want to have an additional profile on tooth number 3 left flank and on tooth number 8 right flank. So we are extremely flexible in definition of where to check the gear, how to check it, and how the modifications look like. So I think I cannot imagine that there is something missing you can't do with that possibilities for definition of T selection in that case. Another nice feature is, so sometimes people want to check a normal profile check, let's say 3 T's on the gear, but they want to have an additional distortion check, let's say on tooth number 6. So I right click on that one. Now this is a special tooth. Now on the other T's, I check one profile of the middle of the tools, left and right flank. On that one, I can say, okay, I want to have 3 profiles, let's say at -5, 0, and +5. Typically, this is called a distortion. So when you go here, you have 1 profile, you see? And if you go to this tooth, you have 3 profiles. So 1 profile on these teeth and 3 profiles at that tooth. You can add another special tooth if there's some need. So it's always up to you what you want to do. So I just right click and say, yes, this is a normal tooth again. It's a normal tooth again. Okay, this is back. So you see, it's pretty easy to define a standard. Just say, okay, 3 teeth. But if you have special requirements, it's very easy to define them. Let's continue to the Helix. Same principle here. The measurement range and the evaluation range here, and the number of teeth to check. And in the Helix, typically it's a V-circle diameter where you want to check the Helix, and you can add as many Helix checks as you want. So we also have the modifications for crowning or reliefs on the end reliefs on the Helix, and yeah, otherwise the same things as on the profile. So let's continue. There's too much here. So this is a pitch run out tip root data page. You select the pitch run out check where you want to check it. Typically it's in the middle of the gear and on the V-circle diameter. But you may add a second pitch run out measurement, let's say at +5 millimeter and at 34 millimeter diameters. So it's always up to you. So you can do this in one measurement. You say, okay, one measurement at 0 at that diameter, the second measurement at +5 at that diameter. Just delete it easily. You see here the ball diameters. So the ball diameter must be clear for the run out evaluation, for the size of our balls and the size of our pins, and also the span teeth, the number of teeth where the span teeth measurement should be taken has to be defined. These are the values to do that. And if you go to that measurement at that position, at that diameter, you can say, okay, I want to have that tooth thickness, size of a ball, size of a one ball, size of a pin, span size, and so on with the nominal values and the tolerances which are allowed for each of this value. So with that page, you can define the pitch run out and the nominals and tolerances for the sizes for balls, pins, span teeth, and so on. And all the same principle for tip diameter check and root diameter check. You can say, okay, 3 teeth, now the tip diameter is checked at tooth number 147. I don't want that one. You can say, okay, at the middle of the gear or another Z position. Always the same like on the other pages. The same with root diameter check. You select the gap where you want to check it. Let's say we have 4 gaps, and these are gaps 1, 3, 6, and 8, and you want to do the root diameter, which should be that nominal value with that tolerance at that position. Say none, nothing happens. Okay, that's the geometric data, nominal data of the gear. And the last page I want to show you is a tolerance page. So typically you have one evaluation standard for the whole gear. Let's say this is a DIN standard, and we have required quality of 6, for example. In that case, all these characteristics, all profile characteristics, Helix, pitch run out characteristics, will have the quality class, required quality class number 6. But if there's a need, let's say, the Helix must not be that exact. So I would say Helix is 9. Okay. Now all the other characteristics are 6, but the Helix is 9. It's a lower quality. Or you would say, nay, the Helix is something special for me. I want to have individual tolerances. This is not 32, this is 31 for some reason. So to summarize this, you can have a quality class for the whole gear. You might have different quality classes for the profile, Helix, and pitch run out. And you may have individual tolerances for each of these characteristics you can define by yourself manually if there's a need. Okay, so now we've defined the gear. We may save it and we'll start it. You click here, you select a probe system, and the measurement will start. Nothing else more is needed. So I have no measure. I'm not at the machine here, so I cancel the measurement. And I want to show you some pre-recorded measurements which were taken on a LH87. So just a second. For example, this one. So this is a typical feed-in cycle. So the probe tries to find the gap. It contacts the flank. Now it rotates the gear a little bit, and now it goes down. Now it reaches the diameter it wants to have, pulls a little bit back, and it contacts the right flank. You see this this red mark marks the tooth number 1. So it contacts the right flank of tooth number 1 and the left flank of the other tooth. So now we have the tooth, the gear coordinate system. Now the measurement starts. So it starts with a lead check, and it has a lead check. Okay, after that it continues with a profile check on the right flank of tooth number 1. And after that, you can see it clearly, but it does another check. So the last check here is that's a pitch check. And this means when we are ready, so when we have one revolution, 1/360 of the gear, all the measurements you've chosen are perfectly made. So no need for another revolution to do a pitch check or so. So just we finished the revolution, 360 degrees, everything is done. I'll speed this a little bit up. You see, the gear rotates, we do the checks, and it continues. So that's the measurement with a rotary table. And I'll have one. Where's that? Oh, here, sorry. And this one is without rotary table. It's the same feed-in process. So I'll try to skip that. And remember, this gear is just mounted on a rotary table, but the rotary table is not active. So I skip that. And this is an interesting point here. So we could check until here with a first probe, and then it's pulled back. We swivel the probe, and then we continue the other teeth. So this is done fully automatically. It's no need for help for you. This is done automatically, so we can check the gear completely with the swivel capability of the probe head. So I've shown you a data entry. We've seen some real-world measurement, and now the gear analyzer comes into play. So the gear analyzer analyzes and presents the gear measurement results. It is based on a GDE file interface, which means gear data exchange format. And this is the open VDE Standard 2610. It's a standalone application, or it can be coupled to a gear. It evaluates according various standards. It has some extensive numerical digital filtering supports. It's highly configurable, and it also has a capability of modify evaluation without the need of new measurement. And it may be used on gear checkers, but it also may be used on production machines like hobbing or grinding machines, which can produce GDE files from internal measurement equipment. It may be used on optical machines, CT machines, any machine which can produce this gear data exchange format can be evaluated and presented. So that was too fast. So I'll show you just a little bit of the gear analyzer. So let's assume this is the measurement we've taken before. And this is a measurement sheet, this is a diagram. And what we use a technique we call, this is an interactive diagram. So if you go, for example, to the magnification, just use your mouse wheel to increase or decrease magnification. Go to the dilation, just use your mouse wheel to increase decreases. Same, of course, on the lead. So it's very easy to make the data the diagram look like as you want it. You see, this is a German. This is the German language here. So perhaps you're a German operator, but you want to produce an English diagram for your American customer. So just switch the language, and you have the English language available on the diagram. It takes a second. Okay, you see now it's an English diagram. Oh, for example, yeah, let's assume this is an American customer. So you are used to millimeters. That's what we in Europe are used to. But your American friend has inches. Just go to this field, use one click of your mouse wheel and switch the diagram to inch. You see, this is inch now. And now for inch diagram, all the values are now in tenths. And we have an inch background here, and everything is converted to inch. Go back to millimeters, so which are more convenient with, and you will have the millimeter diagram back. So just switching force between millimeter and inch is just a mouse click. Or let's say we want to analyze this one here. Yeah, this looks pretty rough, but this is a 5,000 times magnification. Let's play a little bit. Let's say, okay, this EAP is too short to the tip. So let's modify the EAP, let's say, to 90 millimeters. Okay, now the EAP is back to 90 millimeters. You can do this left and right flank same or different like you want. Or if you see the roughness here, looks rough, but remember this is 5,000 magnification. If you want to play, for example, with a filter, say, okay, this is a Gauss filter, and modify the cutoff length. Whoop, you see, it's much smoother now because he modified the filter characteristics. You see, and it's also marked on the diagram. Or you say, I want to have this diagram a little bit more clear. Let's say, okay, I want to have a diagram where the profile and the lead has its own presentation. So just switch to that presentation. There are a lot of available, and have larger diagrams you can work on, you can print, you can send, or you can do what you want. So now you can increase the dilation here. So you have a nice large diagram here on one screen for the profile and one for the lead. And a lot of things you can do after the measurement without doing an additional measurement. So let's continue here. So you've seen a gear analyzer example. And yes, so we are here at the summary. So the gear analyzer together with the gear together with the gear analyzer is an innovative, highly flexible software package for data acquisition, measurement, and evaluation of involute gears on Wensel CMMs. And this is pretty important. The software is completely developed by Wensel and is completely Wensel owned. And all of the typical lead, profile, pitch, and run-out characteristics can be determined, and the operators may use the extensive possibility of Quartis, for example, for the probe management, calibration, workpiece coordinate system, determination, rotary table system without additional training effort. And the communication between gear and the gear analyzer is based on the open GDE standard VDI VDE Guideline 26.0. So, thank you for your attention. My name is Walter Kovacic, and if you have some questions, please visit us at the booth, at the software booth, and I may answer your individual questions. Thank you for your attention again, and have a nice day. Thank you.